So in this video we are going to continue with moles and we're going to look at how moles are used and why they are used every day by chemists. And you'll see that they're typically used when you are carrying out a chemical reaction in order to calculate the exact quantity of reagents that you would need or the quantity of the product that you are going to produce. So we'll have a look at a chemical reaction. I've got a reaction here between carbon and oxygen to form CO2. This equation is already balanced. I've got one carbon on each side. I've got two oxygens on each side. Because I haven't had to put any big numbers in front of the carbon or the oxygen, you can assume that you've got a 1:1 ratio. And what that would mean that if you had one atom of carbon, you would need to react it with one molecule of O2. If you had 100 atoms of carbon, you would react with 100 molecules of O2. And again, that's because you've got a 1:1 ratio. You need the same number of atoms of carbon as you have molecules of O2. Other reactions, you don't have that 1:1 ratio. So I've got an example of one here, the reaction between magnesium and oxygen. To balance this equation, I needed to use a large 2 in front of the magnesium and in front of the magnesium oxide to give me 2 magnesiums on each side and 2 oxygens on each side. This then gives me a ratio of 2:1. So you use the large numbers in the equation to work out the ratio. Big number 2 in front of magnesium, no number in front of oxygen is just a 1. So I've got a 2:1 ratio. And what this would mean is that if I had 2 atoms of magnesium, I would just need 1 molecule of oxygen. And if I had 100 atoms of magnesium, I would need 50 molecules of oxygen. So because you've got that 2:1 ratio, you always need twice the amount of magnesium as you have of molecules of oxygen. So if we go back to another 1:1 example, so I've got iron here reacting with sulfur to give me iron sulfide. Again, this equation is already balanced, so I've just got a 1:1 ratio between iron and sulfur. So again, this ratio tells me that if I had 1,000 atoms of iron, I would be reacting it with 1,000 atoms of sulfur. But if I was actually carrying out this reaction, I wouldn't know the amount of atoms that I was starting out with. I wouldn't be able to measure out 1,000 atoms of iron. Instead, what I'd be doing is I would be getting the mass of iron. So I would use my mass balance and I would get the mass of a certain quantity of iron. And let's just say I wanted to start with 50 grams of iron. I now need to work out how much sulfur I would need to react if I had 50 grams of iron. And what you might do is you might just assume, well, you've got a 1:1 ratio. I need an equal number of iron atoms and sulfur atoms. Therefore, if I've got 50 grams of iron, then surely I just need to react that with 50 grams of sulfur for the reaction to take place. And that is not true, okay? Yes, you need the same number of atoms, but that doesn't mean that you need the same mass of iron and sulfur. And I'm going to use just a simple example below to hopefully illustrate why that is the case. So rather than explaining this through a chemical reaction, we're going to look at something far simpler. I'm going to look at the exercise books that we use in school and the covers that we put on those books. We need the books and covers in a 1:1 ratio. So if I wanted a class set of 30 books, I would want 30 covers so that each book had a cover to go with it. So let's just say I want 30 books and 30 covers, but I go onto the website to order these books and it doesn't let me specify how many books I want, doesn't let me specify the number. Instead, I have to specify the mass of the books that I want. So I decide, okay, I'm going to order 300 grams of books. Am I also going to order 300 grams of covers? Remember, I want the same number of books and covers. So if I'm ordering 300 grams of books, am I also going to be ordering 300 grams of those plastic covers? The answer is no, okay? I'm not going to be ordering the same mass of covers. And the reason is that each cover is lighter than each book. So if I want the same number of books and covers, because covers are so much lighter, the mass of 30 covers is not going to be the same as the mass of 30 books. The mass that I'm going to be ordering of those covers is going to be a lot smaller. So if I actually wanted to work out the mass of the covers that I needed to order, the first thing I would need to do is figure out, well, if I'm ordering 300 grams of books, how many books am I actually ordering? So if I have a little search on the website, I find out that each book has a mass of just 10 grams. So if I'm ordering 300 grams of books and each book has a mass of 10 grams, well then how many books am I ordering in total? So I would have to do 300 divided by 10, and I realised that I am indeed ordering 30 books, which is exactly what I wanted. Now I know that if I'm ordering 30 books, that I also want to order 30 covers. But that does not mean that I'm going to be ordering 300 grams of covers. I need to know the mass of each individual cover. And let's say each cover is only 5 grams. Because each cover is only 5 grams, I know I want 30 covers. So I'm going to have 30 multiplied by 5. I'm going to have 150 grams of covers. Okay, so I want the same number of books and covers, but the mass I order is going to be different because covers are lighter than books. The total mass is not going to be the same. And that's going to be exactly the same with my chemical reaction. The mass of an iron atom and the mass of a sulfur atom is not the same. If I go to my periodic table, I will see that a mass of an iron atom is 56. The mass of a sulfur atom is only 32. So the iron atoms are far heavier than the sulfur atoms. Therefore, if I want iron and sulfur present in equal quantities, then I'm not going to be reacting them in equal mass. Okay, and I'm going to need to figure out, well, I know I'm not going to be using 50 grams of sulfur, but I want to figure out if I'm reacting 50 grams of iron, how much sulfur will I need in this reaction so that I have the same number of iron atoms and sulfur atoms. So I'm going to do out this calculation, and it's going to be very similar to the calculation I just did with books and covers. So I've got iron and sulfur. From my chemical equation, I could see that I've got a 1:1 ratio. So my ratio between the two of them is 1:1. I know the mass of iron I want to react is 50 grams, but I'm going to need to work out how much sulfur I need to react with 50 grams of iron so that I've got the same number of atoms for each. So when I was doing this with books and covers, I knew the mass of books that I was ordering, but I wanted to find out the mass of each individual book so I knew how many books I was ordering. I'm basically going to do the same here. I need to know the mass of each individual iron atom, and we typically call this formula mass. So if I've just got one iron atom, from my periodic table, I can see it's got a mass of 56. Okay, the next thing I did with my books was I took the total mass that I was ordering and I divided it by the mass of each individual book to find out the number of books I was ordering. And I'm going to do the exact same here. I'm going to take the mass, I'm going to divide by the formula mass. So I'm going to do 50. Make sure I can get rid of this now. I can do 50 divided by 56, and when I do that, bear with me a second, I do 50 divided by 56 and I get 0.89. We've seen in the previous video that when you do mass divided by formula mass, you are not finding the individual atoms, you are finding the number of moles. So the mass divided by the formula mass does not tell me how many atoms I've got. If I've got 50 grams of iron, I've got way more than 0.89 atoms. Atoms are absolutely tiny. So if I've got 50 grams of iron, I would expect a huge number of atoms. So when I do mass divided by formula mass, I'm not finding the individual number of atoms, I'm finding the number of moles of iron that I have got. However, once I've got my number of moles, I can then use that to find out the number of atoms. So I now know that I've got 0.89 moles of iron. I know that the word mole represents the number 6.02 by 10 to the 23. So if I want to know how many individual atoms of iron I have got, I do 0.89 multiplied by 6.023 by 10, 6.02 by 10 to the 23, and I end up with 5.36 by 10 to the 23. So if I know how many moles of iron I've got, I can find out how many atoms of iron I have got. So I know now that this is the number of atoms of iron that I have. I know that I need to have an equal number of sulfur atoms. So if I've got this many atoms of iron, then I want this many atoms of sulfur. Rather than working with these numbers, which are large and awkward, if I have 0.89 moles of sulfur, I know that if I have 0.89 moles of sulfur, then the calculation to find out the number of atoms of sulfur would be exactly the same, giving me the same answer. So if I have an equal number of moles, then I have an equal number of atoms. So rather than dealing with these large numbers and dealing with standard form, I can just go 0.89 moles of iron. I also want 0.89 moles of sulfur, because when I convert from moles to atoms for both of them, I get exactly the same number of atoms, which is what I want. I want them present in equal quantities. So if I've got 0.89 moles of iron, I want the same number of moles of sulfur. So this is the number of moles of sulfur that I want. Formula mass of sulfur I can fill in from my periodic table is 32. And just like I did here with the covers, I knew the number of covers that I wanted, I knew the mass of each individual cover, then I did 30 multiplied by 5 to get the mass. I know the moles of sulfur that I want, I know the formula mass of each sulfur atom, so I'm going to do 0.89 multiplied by 32, and I'm going to get 28.48 grams. So if I've got 50 grams of iron, I only need 28.48 grams of sulfur. I do want an equal number of atoms, but because each iron atom is heavier than each sulfur atom, this number of iron atoms is going to have a greater mass than the same number of atoms of sulfur. So I can't just assume 50 grams of iron is 50 grams of sulfur. I have to actually work it out. And this is where moles becomes really, really useful. You need to know how many atoms you've got in a given mass, but calculating atoms means dealing with really large numbers. Rather than dealing with those really large numbers, you can just stick with moles, because if you've got the same number of moles of two different elements, then you do have the same number of atoms. It would be the same if I said you've got 5 pairs of shoes and 5 pairs of socks. You know that if you've got 5 pairs of each of them, that you've got the same number. You don't need to work out that 5 pairs is 10 shoes and 5 pairs is 10 socks. You straight away know if you've got 5 pairs of something and 5 pairs of something else, that you've got the same overall number. And it's the same here. You know the number of moles, you know you want the same overall number of atoms, so just make the number of moles the same, and then you can work out the mass that you need. So as well as using moles to work out the mass of your reactants, you could also use moles to work out the mass of product that you are going to make. So in this equation, I've got lithium reacting with fluorine to give me lithium fluoride. I'm starting with 31 grams of lithium, and I want to know, well, what's the mass of lithium fluoride that I'm going to produce if I'm starting with 31 grams of lithium and I've got enough fluorine to drive this reaction to completion. So again, I can work this out using moles. So what I can't do, all right, if I look at the ratio here, I've got a 2:2 ratio, which I can be simplified to 1:1. But I can't just say, oh, 1:1 ratio, 31 grams of lithium is going to give me 31 grams of lithium fluoride, okay? It's not. I need to work out I need to work out exactly how much lithium fluoride I'm going to produce. So to do this, I'm going to draw out the same table that I had before. I am given the mass of lithium, and I'm trying to find out how much lithium fluoride that I am making. I'm not asked about fluorine. I'm not given information about fluorine. So for the rest of this question, I can ignore the fluorine and just focus on the lithium and the lithium fluoride. I'm given the mass of lithium as being 31 grams, and the mass of lithium fluoride produced is what I'm trying to find. If we've got mass, I can always calculate formula mass using the numbers from the periodic table. So you will be given this in the question. Lithium, the mass of lithium is 7, the mass of fluorine is 19, and you'll get that from the periodic table. So I want to get the formula mass of lithium. I've only got one lithium, so the formula mass is just going to be 7. If I want to get the formula mass of lithium fluoride, then I've got 7 for lithium, I've got 19 for fluorine, I've got a formula mass of 26, okay? When you are calculating formula mass, you do not use these big numbers from the equation. So you do not multiply 7 by 2 or 19 by 2. Once you've got mass and you have got formula mass, you are able to find moles. Remember, mass divided by formula mass equals moles. So I've got the mass of lithium, 31. I've got the formula mass of lithium is 7. I divide and I get 4.43. I can't do the same for lithium fluoride. I can't work out the moles because I don't have the mass. So I'm not able to fill in that box for lithium fluoride. But what I do have is my balanced equation, which provides me with the ratio. So to find out the ratio, this is when I use the large numbers. The big number in front of lithium is 2. The big number in front of lithium fluoride is also 2. So my ratio is 2 is to 2, but I can simplify that to 1 is to 1. So again, I've got a 1 is to 1 ratio, which means that if I'm starting with 4.4 moles of lithium, I am going to be producing 4.4 moles of lithium fluoride. 1 is to 1 ratio. If these two numbers are the same, then the number of moles will be the same. 4.4 moles of lithium will produce 4.43 moles of lithium fluoride. But 31 grams of lithium gave me 4.43 moles. I need to work out the mass of lithium fluoride if I've got 4.43 moles, okay? And I'm expecting it to be more. I'm expecting the mass to be greater because I'm reacting lithium with fluorine, so the mass of the product should be the sum of the mass of both of my reactants. So I'm expecting the mass to be a lot bigger than 31 grams, and it's going to be. So if I have the number of moles, 4.43, and I want to find out the mass, I have to multiply by formula mass. So I get 4.43 multiplied by 26, and I get 115.18 grams. That's how much lithium fluoride I am producing. So the number of moles is the same, but you can see the mass of lithium fluoride is much greater because you've got a greater relative formula mass. I'm going to do another one of these with you. I'm going to write a different equation. Calcium plus water goes to CaOH2, which is calcium hydroxide, and H2. And let's assume that I'm starting with 60 grams of calcium, and I want to know how much hydrogen I am making. So in this equation, I've got quite a lot going on. I've got 2 reactants and I've got 2 products. But when I'm drawing my table, I'm only going to be including 2 things. I'm given information about calcium, so calcium's important. It's going to be in my table. I'm asked about hydrogen, so hydrogen's important. It's going to be in my table. I'm ignoring water. I'm ignoring calcium hydroxide. I'm only ever going to have 2 things in my table. I put mass in first. I'm given the mass of calcium. I fill that in straight away. I don't have the mass of hydrogen. That's what I'm trying to find. After mass, I get formula mass. Again, I go to the periodic table for this. The mass of calcium is 40. The mass of hydrogen is 1. So I'm going to have 40 there for Ca because I've just got 1 Ca. The mass of each hydrogen is 1, but if I look at my formula, H2, okay, I've got 2 hydrogens, so it's going to be 1 plus 1 equals 2. So when you're getting formula mass, you are using the small numbers, you're just not using the big numbers. We use big numbers for the ratio, we use small numbers for the relative formula mass. So there's no small numbers around calcium, it's just going to be 40, but H2, I've got 2 of them, giving me a formula mass of 2. Have mass, formula mass, next up is moles. To find moles, it's mass divided by formula mass, it's going to be 60 divided by 40, and that's going to be 1.5 moles. Again, I can't do the same for hydrogen, but I have got my ratio. Ratio, I use the big numbers. There's no big number in front of calcium, so I write down a 1. There's no big number in front of hydrogen, so I also write down a 1. I've got a 1:1 ratio. That tells me that if I had 1.5 moles of sodium, I would be producing 1.5 moles of hydrogen. If these numbers in the ratio are the same, then the number of moles are going to be the same. Now I know the number of moles, I know the formula mass, it's going to be 1.5 multiplied by 2, 3 grams. If I've got 60 grams of calcium, I'm going to be producing 3 grams of hydrogen. I want you to have a go at the following 2 questions yourself. So I've already drawn the table for you and I've filled in parts of it. All you need to do is fill in the remaining 3 boxes on each table. So press pause, have a go, and press play when you're ready to see the answers. So I've filled in the answers here. Okay, so the first one you should be doing 100 divided by 74. Because you've got a 1:1 ratio, the number of moles is the same for both. Once you know the moles of calcium, you multiply by 40, you get 54.05. Here you've got 132 divided by 18 to give you 7.3. Again, the ratio is the same, 1:1 ratio, so you're going to have 7.3 moles of both, multiply by 56, and you get the mass of KOH. So in all of the examples we've looked at so far, we've had a 1:1 ratio. So in the next example, we're going to have something a bit different. So in this equation here, let's get rid of this. In this equation here, I'm starting off with 132 grams of water, and I want to know how much hydrogen gas am I going to produce. Again, I've got lots in my equation, but I'm given information about H2O, so that's important, and I'm asked about H2, so that's all I'm going to include in my table. I always start off with mass. I'm given the mass of water as 132 grams. I'm trying to find hydrogen. Formula mass of water, again, I need to work this out. The mass of an oxygen atom is 16. The mass of hydrogen is 1. So I've got H2O, so I've got 1 plus 1 plus 16 equals 18. Okay, 2 hydrogens and 1 oxygen is 18. Remember, I do use the small numbers working out formula mass, but I do not use the large numbers. For H2, 2 hydrogens, each with a mass of 1, gives me a formula mass of 2. For doing moles, it's going to be mass, which is 132, divided by formula mass, which is 18, and I'm going to get 7.3. I now need to do ratio. And ratio, I do use the large number. So the number in front of water is a 2. The number in front of hydrogen, there is none, so it's 1. So this is the first example we've seen where we haven't had a 1:1 ratio. Now we've got a 2:1 ratio. So what this tells me is that if I had 2 molecules of water, I would only be producing 1 molecule of H2. If I had 10 molecules of water, I'd be producing 5 molecules of H2. I'm always producing half the amount of hydrogen. So I can see here that I've got 7.3 moles of H2O. I know I'm only going to be producing half the amount of hydrogen, so it's going to be 7.3 divided by 2. I'm only going to be making 3.6 moles of H2. So these ratios have to be the same. 1 is half of 2, 3.6 is half of 7.3. Now I know the number of moles of hydrogen I've got, so it's going to be 3.6 multiplied by 2, and I get 7.3. So if I started off with 132 grams of water, I'd be producing 7.3 grams of hydrogen gas. So I want you to have a go at the following two questions yourself. Again, you've got a 2:1 ratio in both cases. So have a go at doing questions 7 and 8. Press pause, do them, and then press play when you're ready to see the answers. All right, so I've filled in the answers. So the first one, you're going to do 50 divided by 39 is 1.28. That's the number of moles of potassium. Because you've got a 2:1 ratio, you're only going to produce half the amount of hydrogen. So I need to find half of 1.28. So I divide 1.28 by 2 and I get 0.64. If I've got 0.64 and the formula mass of hydrogen is 2, it's going to be 2 times 0.64 and I end back up with 1.28 grams of hydrogen being produced. The reaction below, start with 50 grams of hydrogen, formula mass of 2, so I've got 25 moles. The ratio here, 1:2, so you're producing twice as much hydrogen. So I need to multiply 25 by 2 to get 50. And then it's 50 times 39 is 1950. So just make sure the ratio is the same each time, all right? Here, this number 2 is twice this number 1, so the ratio for moles has to be the same. The number above the 2 should be twice as big as the number above the 1. Down here, you've also got a 2:1 ratio, but you worked out the hydrogen first, and when you're working out the moles of potassium, it has to be twice the amount. So the ratio here, 2:1, here 50 to 25. Make sure you haven't done that the other way around. Also, just to say, if you're getting kind of different numbers than me, so 50 divided by 39, you should have an answer when you do the first one of 1.28. And then when you do 1.28, divide that by 2, you get your what? Actually, no, I think it should be okay. Sorry, I was just going to say, I usually give my answers to 2 decimal places. Sometimes what can happen is if you were writing this down, so 50 divided by 39, you get an answer of 1.282051. I've just written this down as 1.28. And what you can do is you can either not clear your calculator and divide by 2, and then multiply that. Well, you're still going to go back to where you were. Actually, this isn't a very good example of it. But my point is, typically what I do is when I'm dividing, I don't clear my calculator. I write down what the answer is to 2 decimal places, but I don't clear my calculator, and I'm doing my further calculations with the longer, more accurate number. So if you're getting a slightly different answer to me in some of these cases, it may be because you are clearing your calculator after each calculation, therefore you're getting a less accurate answer at the very end. Right, I'm going to get you to the following 2 examples. So far I've been filling in a lot of the table for you. In these 2 questions, I'm not. Okay, so I filled in the side and the top, but all of the numbers you're going to have to fill in for yourself. So when you're calculating formula mass, use these numbers up here at the top. When you're doing ratio, you're going to use your balanced equations. So have a go at 12 and 13. Try and fill this information for yourself. Press pause, press play when you're ready to see the answers. So here are the answers. All right, so you have 80 grams of oxygen. You work out the formula mass of O2, so it's going to be 16 plus 16 is 32, and then it's mass divided by formula mass to get moles. Your ratio is going to be 1:2. There's nothing in front of oxygen, so you get a number 1, and in front of Li2O, you've got a 2. That means if you had 1 mole, you would produce 2 moles, so you're doubling. So if you've got 2.5 moles, you're going to multiply by 2 to get 5 moles of lithium oxide. Formula mass of lithium oxide, you've got 2 lithium, so 7 and 7 is 14, plus the 16 for the oxygen gives you 30. It's going to be 5 times 30, 150 grams. Below, we have 50 grams of calcium sulfate. You work out the formula mass of calcium sulfate, so you've got 1 calcium, 1 sulfur, and 4 oxygens using these numbers. You should get 136. You work out the number of moles. The ratio in this case is 1:1. There's no numbers in front of the CaSO4 or the CaO, so it's just 1:1. So if these numbers are the same, then these numbers will also be the same. Formula mass of calcium oxide should be 56, so 40 from the calcium, 16 from the oxygen. You multiply these 2 and you get the mass of calcium oxide. I'm just going to get you to have a go as well at just 3 more questions. This time I have not drawn the table at all, and I've just included a little bit more kind of extra information, as that's all often how they appear in the exam. Don't get distracted by the words. The questions are all done exactly the same way. If you draw out your table, you won't go wrong. So you'll have to practice drawing it out for yourself. You need to pick out what's relevant from the equation. You'll need to calculate your formula mass yourself, work out the ratio, all of it. But have a go at 17, 18 and 19. Again, press pause, press play when you're ready for the answers. I'm just going to go through these answers. So here's your first equation. You have got iron and you have got iron chloride. They tell you you've got 11.20 grams of iron. You can work out the moles of iron by dividing by 56. For your ratio, you've got a large 2 in front of both. It gives you a 2:2 ratio, which you can simplify to 1:1. If you've got a 1:1 ratio, then the number of moles will be the same for both. And then you take the number of moles, multiply by the formula mass of iron chloride. So you've got 1 iron and 3 chlorines. It should work out as 162.5. Multiply these two numbers and you get 32.5. In the next one, you have got nitrogen and hydrogen reacting to give you ammonia. You're asked how much nitrogen is needed to produce 72 grams of ammonia. So you find out the moles of ammonia you're trying to produce. So it's going to be 72 divided by 17. So you've got 14 for nitrogen and 3 for the 3 hydrogens. Formula mass is 17. You work out the number of moles. Then you use your ratio. You've got a 2 in front of ammonia. You've got nothing in front of nitrogen, so it's a 1. So you've got a 2:1 ratio. So you're going to be producing half the amount. So 4.24 divided by 2 gives you 2.12. Multiply this by 28, so it's N2, 14 and 14 is 28, and you work out the mass of nitrogen. And the last one, you have got sulfur and fluorine giving you SF6. You're told that you've got 0.950 grams of fluorine. They actually give you the formula mass, so you can just divide and find out the moles. You've got a 3:1 ratio, so a 3 in front of the fluorine, nothing in front of SF6. So 3:1, so your fluorine is 3 times the SF6. So I need to divide by 3, okay? This is 3 times less, so this has to be 3 times less. I divide by 3. Once I divide by 3, I then multiply by the formula mass. Again, you're given that in the question, and I end up with the mass that's going to be produced. So you may have noticed in some of these questions that the way they phrase things. So here, calculate the minimum mass of nitrogen. It doesn't make a difference. You're doing it in exactly the same way. Down here, it talks about, just makes it longer. They talk about reacting with an excess of sulfur. You're not given any information about sulfur. You're not given a number. You're not asked about sulfur. So you're still just focusing on the fluorine and the SF6. So don't be distracted by the language they use in the question. The method is going to be the same every single time, even when it appears harder.